essential building blocks, and then food preservation, which is really the chemistry of stability.
Exactly. And the mission here is to transform this stack of source material, which is full of clear definitions and chemical examples, into high-level practical insight for you.
Right. For those of you who need to get up to speed quickly but also thoroughly, this deep dive is structured like a syllabus. We're going to be connecting the molecular, the atoms and bonds directly to the things you can see and touch.
So we'll break down definitions, classifications, properties, applications, the whole 9 yards. It's all about connecting the architecture of a molecule to, say, why your plastic bottle is different from your non-stick pan.
Or why salt preserves meat better than water does.
Yeah.
Yeah.
Think of this as your course plan. We'll start by defining polymers and looking at how they're classified.
Okay.
Then we'll dive into some really detailed case studies of synthetic materials. Polythene, Teflon, nylon, and we'll see how tiny changes in the process or structure create completely different materials.
And after we've got a handle on the chemistry of physical structure, we're pivoting.
Completely. We'll pivot to food chemistry. We'll look at how spoilage happens, both from microbes and chemical reactions like rancidity, how we prevent it. And then we'll wrap up with a critical look at the really complex world of artificial sweeteners.
All right, let's get into it. Let's start with our first foundational module, polymers. The fundamental building blocks. And if you just pause for a second and look around whatever room you're in, I guarantee you are surrounded by them.
Oh, absolutely. Silk, wood, the fibers in your clothes, natural rubber.
And, of course, every single piece of plastic you can see. They're all polymers. It's really not an exaggeration to say it's pretty much impossible to imagine modern life without them. But to do this right, like a proper class, we need to start with vocabulary. We need to be speaking the same language.
Right. The word itself, polymer.
Yeah, the term polymer is rooted in 2 Greek words, poly, which simply means many.
And mer, which means a unit or a part. So many units.
Exactly. And when we talk about them formally, chemists refer to them as macromolecules.
Because they're huge.
They're massive. The definition of a polymer is a high molecular mass substance. We're not talking about small, simple molecules here. These typically have masses from 10 to the power of 3 up to 10 to the power of 7 atomic mass units.
That is an enormous, complex structure.
And that huge structure is what gives it its properties.
Yeah.
But crucially, the structure is repetitive. Each polymer molecule is made of a very large number of simple, repeating structural units.
The
monomers, exactly. Imagine chemically identical building blocks just joined end to end by strong covalent bonds, forming these incredibly long chains or sometimes complex 3-dimensional networks.
And what's really amazing when you first learn this in chemistry is that these aren't just things made in a lab. They are the foundation of life itself. We're not even talking about plastics yet.
No, not at all. Every living thing on this planet is built from biopolymers. If you're breathing, you're based on polymers.
Wow.
Carbohydrates, which give us energy and structure, are polymers of simple sugars. Proteins, which are responsible for, well, almost every chemical reaction and structure in our cells, are just polymers built from amino acids.
And DNA, of course.
And of course, DNA and RNA, which carry our genetic blueprints, are polymers of nucleotides.
To give some specific natural examples, the structural integrity of a tree or any plant that's dependent on the polymer cellulose.
Right. And if you look at us, at animals, things like feathers, fur, hair, even our fingernails, they're all made of the protein keratin. Nature figured out how to build massive, durable, flexible, and functional materials using polymerization long before we did.
So how did we make that leap? The move from just using natural polymers to creating our own synthetic ones is, well, it's a fascinating story.
It is, because synthetic polymers now form the basis for all our artificial fibers, synthetic rubbers, and the plastics that underpin, well, everything in modern industry.
And the breakthrough wasn't some grand plan discovery, was it?
Not at all. The very first synthetic polymer was created by accident, really. It was just a byproduct of another chemical reaction. Early chemists would see this sticky, thick gunk forming.
Just throw it out.
Just throw it out, assuming it was useless waste. They couldn't see the potential in that chemical structure.
But then along comes Leo Baekeland.
Yes. And here's where the story turns. He recognized the potential in this seemingly worthless gunk. Through very controlled reaction conditions, he developed what we now know as Bakelite.
And Bakelite was a game changer because it was the first true thermosetting plastic.
What does that mean, thermosetting?
It means that once you molded it into a shape using pressure and high temperature, it became permanently rigid. It was set. You couldn't melt it or change its shape again.
Right. And this discovery just transformed manufacturing. It gave us durable, heat-resistant materials that were used for everything from the classic black telephones and old radios to, very importantly, electrical insulation.
It really was the dawn of the synthetic age.
It truly was. So now let's get into the classification, which is crucial for organizing all this. We can categorize polymers in two main ways. The first is based on the source, where the material came from.
Classification by source. Okay, so that gives us three types. The first is the most straightforward, natural polymers.
Right. These are just obtained directly from plants and animals. We already mentioned a few. Proteins, cellulose, starch, natural rubber.
Okay, second, we have synthetic polymers. These are entirely man-made, usually in industrial settings, and they're the focus of so much of modern chemistry.
Yeah, that's your polythene, your nylon 6, your polyester, all the common plastics that you interact with every single day.
And the third category is sort of a bridge between the two, isn't it?
It is. Semi-synthetic polymers. These are polymers that we start with from nature, but then we chemically modify them in a lab to significantly improve their properties for certain uses.
And the classic example you brought up earlier is natural rubber.
Exactly. It's a natural polymer, but on its own it can be a bit sticky and not very durable. But when we chemically modify it through a process called vulcanization, we create something much harder, stronger, and more temperature resistant.
Something you can make a tire out of.
Something you can make a heavy-duty tire out of. Precisely.
Okay, so that's classification by source. What's the second way we classify them?
The second way is based on the nature of the repeating structural unit, which is fundamental to predicting the polymer's final properties. This gives us two major types based on the monomer, the building block.
Right. The first one is a homopolymer.
Which is the simpler structure. The entire polymer chain is built from one single repeating type of monomer. That's it.
For instance, polythene is a homopolymer. You just take a huge number of ethene molecules and link them all together into one long chain.
One after another. That's a homopolymer.
Yeah, you compare that to a copolymer.
And these are more complex. Their repeating units are made from two or more different types of monomers, which can be alternating or just randomly distributed along the chain.
And this mixing of the monomers lets chemists fine-tune the final properties of the material much more effectively, I'd imagine.
Oh, absolutely. It's like having more ingredients to cook with. A key example is nylon 6,6, which uses two very distinct building blocks. This complexity is what allows for some really sophisticated molecular engineering.
Okay, so to wrap up this first module, let's formally define the process itself. Polymerization.
It's the process where those simple monomer units combine chemically to produce that massive chain-like or network molecule we call the polymer. Understanding this fundamental process, the link between the single unit and the complex chain, is absolutely the key.
It's the key to understanding structure and function.
Exactly.
So building on that, let's zoom in on how specific chemical conditions and structural differences can just completely transform a material's performance. We're moving into deep dive 2, key synthetic polymers in daily life.
And this part is so important because we're moving past the definitions and into the mechanism of how these things are made. We're applying that foundational knowledge of structure and linking it directly to how we use these things.
The guiding principle here, then, is that seemingly minor changes in structure or the synthesis conditions can lead to, well, huge variations in property.
Huge variations. And let's start with polythene, the homopolymer of ethene, because it is the perfect illustration of how the manufacturing process completely dictates the final material.
Polythene is split into two classes, right, based entirely on the conditions used during polymerization.
That's right. First, you have low-density polythene, or LDP. This is the older method, and it often uses very high temperatures. We're talking 350 to 750 Kelvin and extreme pressures, sometimes 1,000 to 2,000 atmospheres.
Whoa. So if you're just trying to link ethene molecules together, why do you need such extreme high-energy conditions? What's happening chemically under all that pressure?
That's a great question. Those conditions, they favor a mechanism called free radical polymerization. And this process is inherently less controlled. It's a bit chaotic, chemically speaking.
What does that mean, less control?
It leads to the formation of lots of short reactive side chains that just branch off the main polymer backbone. So instead of a nice straight line, you get this tangled, messy structure.
So the poor packing of these branched polymers naturally results in low density. That makes sense. And their properties must reflect this structural messiness.
They do. They're transparent, they're chemically inert, poor conductors of electricity, but critically, they are soft and slightly flexible. They only have moderate tensile strength. You can stretch them and squish them.
So LDP is for things where you need that flexibility and insulation. I'm thinking of standard plastic grocery bags, film wrap.
Exactly. Insulation for electrical wires, squeeze bottles, flexible pipes. It's the soft plastic of the world.
Okay, now let's contrast that with high-density polythene, HDP. This is a more modern, more controlled process.
Much more controlled. It's manufactured at much lower temperatures, only about 333 to 343 Kelvin, and significantly lower pressures, just 6 to 7 atmospheres. That is a massive difference in the energy you have to put in.
So what's the secret? How do you do it with so much less energy?
The key is the use of specialized catalysts, typically something called Ziegler-Natta catalysts. Think of them as precise chemical instruction sets that guide the ethy molecules to line up perfectly.
So you go from chaos to precision.
Exactly. This controlled environment results in mostly linear polymer chains with very little branching.
And because these linear chains can pack together very efficiently and tightly, the resulting material has a high density.
Right, and this superior packing leads to superior mechanical properties. HDP is translucent, chemically inert, and it is significantly more tough, hard, and tensile than LDP.
It's the tough plastic, so this is what you use for making heavy-duty items like buckets and tubs.
Rigid water and gas pipes, solid bottles that need to keep their shape under stress. This single example, just polythene, shows how a shift from high-pressure chaos to low-pressure, catalyzed precision completely dictates what the material can be used for.
And that structural principle holds for our next examples. Let's look at PVC, or polyvinyl chloride. This is a homopolymer of vinyl chloride. So here we're adding a single chlorine atom to the monomer. That one atom changes everything from ethene.
It really does. That chlorine atom is large and highly electronegative, which means it's polar. And that introduces intermolecular forces that help stabilize the chain.
So what does the final material look like?
The resulting solid is white, brittle, and odorless, with a density of about 1.4 grams per cubic centimeter, which makes it heavier than most polythenes.
And while the base material is brittle, PVC is also lightweight, incredibly durable, cheap to make, and easy to process. And because of that stability from the chlorine, it's insoluble in water and ethanol.
And you see it everywhere. Stability and durability are needed. From rigid plumbing pipes and electrical cable insulation to robust flooring. Its durability also makes it super important in the medical field for things like tubing.
Next up is maybe the most chemically extreme polymer on our list, Teflon, or PTFE, polytetrafluoroethylene.
Right. This is the homopolymer of tetrafluoroethene. So if PVC added one chlorine atom, Teflon replaces every single hydrogen atom on the backbone with a bulky fluorine atom.
And the structure itself explains why Teflon is so famous, doesn't it?
It absolutely does. Fluorine is the most electronegative element, and the resulting carbon-fluorine bonds are incredibly strong. On top of that, the large size of the fluorine atoms effectively creates a shield around the carbon backbone, protecting it from chemical attack.
And the properties are, well, they're remarkable. It's flexible, yes, but it's stable up to almost 600 Kelvin. Incredible thermal resistance.
But its most famous property is its chemical inertness. It is insoluble in almost everything, including boiling concentrated acids, even aqua regia.
Aqua regia, the stuff that's designed to dissolve gold.
The very same. So that incredible chemical resistance and its extremely low friction are what make it perfect for its applications. Non-stick pans, high-performance gaskets, seals, and valves where you just cannot tolerate any corrosion.
You need a material that basically refuses to interact with the world, and Teflon is it.
Teflon is the champion of being non-reactive.
Okay, moving into the world of synthetic fibers. Let's look at PAN, or polyacrylonitrile, also known by its trade name, Orlon. This is a homopolymer of acrylonitrile. Structurally, it has a cyano group, a carbon triple bonded to a nitrogen attached to the backbone.
And the role of that cyano group is critical. It's a highly polar group. And when you have a massive number of these highly polar groups all along a chain, those chains are attracted to each other very, very strongly through dipole interactions.
So that strong attraction between chains makes PAN a hard, horny, and high melting material.
It does. And that high melting point and inherent hardness mean the fibers are extremely durable and they hold their shape really well. This makes PAN fibers like Orlon and Acrylon an excellent synthetic substitute for wool.
So you find it in clothes, carpets, blankets.
Exactly. It provides durability and warmth without the fragility or the cost of natural wool. Again, we see that one small chemical group, the CN group, dictates the entire performance profile of the material.
Next, polystyrene, a homopolymer of styrene. The structure of styrene is significant because it has a very large benzene ring attached to the monomer unit.
That benzene ring is big and bulky, and when you polymerize thousands of these units, these bulky rings get in the way and prevent the polymer chains from packing closely together.
So that bulkiness results in a polymer that is generally clear, rigid, and moderately strong, but also kind of brittle.
Yes, and polystyrene is probably best known for its two completely different forms. The rigid form is used for things like transparent, throwaway drinking cups.
But then there's the foam version, styrofoam.
Right. And for that, we just force gas into it during polymerization. Styrofoam takes advantage of that poor packing caused by the bulky rings, resulting in a low-density material that's filled with air.
Which makes it a fantastic insulator. That's why it's used for ice chests and disposable coffee cups.
Exactly.
Okay, now for our first true copolymer example, where we're intentionally linking two different monomers, nylon 6,6. To really understand its strength, we need to look at the two building blocks.
The two distinct monomers are adipic acid, which is a 6-carbon dicarboxylic acid, and hexamethylene-diamine, a 6-carbon diamine.
And the 6 in the name tells you that each monomer contains 6 carbon atoms.
That's right. And the key chemical insight here is the reaction type. This is not like polythene where monomers just add together. This is condensation polymerization.
Condensation, so what does that mean?
It means that when the acid and the amidamine functional groups link up, they condense. They form a new bond called an amide linkage, and at the same time, they kick out a small molecule. In this case, it's a molecule of water.
Ah, okay.
And the resulting structure is this highly regular chain of amide linkages. Because the chain is so uniform and that amide group is highly polar, the chains can align perfectly. This allows for extensive hydrogen bonding between the chains. It's like molecular Velcro.
And that extensive perfect alignment and the strong secondary bonding. That's why nylon 6,6 is a fiber-forming solid with incredibly high tensile strength. It's crystalline in nature. We literally engineered strength into the structure.
We did, by choosing two specific monomers and forcing them to form these strong, regular bonds. And as a result, nylon 6 is used for making sheets, the really tough bristles for brushes, and of course it's massive in the textile industry where you need durability and strength.
All right, finally, let's revisit natural rubber, the polymer of isoprene, which comes from the latex of rubber trees.
Natural rubber chains are typically coiled up, and they have elastic properties, which lets them stretch easily, kind of like a spring. They also absorb a lot of water.
But that softness and water sensitivity, that limits its use for heavy-duty stuff.
It does. And that takes us back to the concept of semi-synthetic modification we mentioned earlier, vulcanization. This process was the key to making rubber industrially useful.
So what is vulcanization?
It involves heating raw natural rubber with sulfur at around 373 to 415 Kelvin. And what happens chemically is crucial. The sulfur atoms react with the double bonds in the polymer chains and form cross-links.
Like chemical bridges between the chains?
Exactly. They act like internal rivets. They drastically restrict the movement of those coiled chains, which causes the rubber to get much stiffer.
So this modification reduces its elasticity and water absorption and dramatically increases its mechanical strength and temperature stability.
It transforms a soft, sticky material into a tough, durable elastomer that's suitable for everything from industrial hoses and shoe soles to massive, high-performance vehicle tires.
Wow. So we've established that the immense utility of polymers comes from this ability to engineer specific properties, soft, hard, flexible, rigid, all, by controlling the monomer and the polymerization conditions.
Right.
But that structural review leads us straight into our next module. Polymers aren't all good. It's the material paradox of our time. The very stability we engineered for utility now creates a huge environmental crisis.
Yeah, and this section requires some serious critical caution. Despite the phenomenal benefits we've just detailed, the sheer volume is staggering. Millions of tons of plastic are dumped into landfills or pollute our oceans every single year. We built materials to last forever, and now we have to deal with that.
The core chemical problem is that the strong covalent bonds and inert chemical structures, the reasons Teflon doesn't react and polythene doesn't dissolve, also mean that the material just doesn't biodegrade.
Not in any meaningful timescale. Microorganisms, which can break down natural polymers like cellulose pretty easily, they just can't efficiently cleave these synthetic carbon-chlorine or carbon-fluorine bonds.
So instead of decomposing, the plastic just breaks down mechanically. It just gets smaller and smaller into what we call microplastics.
Right. These tiny fragments, anything smaller than 5 millimeters, they persist indefinitely.
And the terrifying implication here is that these microplastics are now everywhere. They permeate the entire biosphere, they affect marine life, they get into the food chain.
And they're now detectable in our drinking water, in the air we breathe, and even in human organs. This persistence means the problem we created decades ago will affect us and many generations to come.
And there are also specific concerns about chemical additives. For example, styrofoam is made mostly of styrene. The Environment Protection Agency has identified styrene as a possible carcinogen.
The concern is that as styrofoam breaks down, or if it's heated, it can release toxic styrene into the environment and potentially into the food or drink it contains.
And it's not just styrene. Other common additives like phthalates, which are used to make PVC flexible, or BPA, which was used in polycarbonate plastics, are known endocrine disruptors. They mess with hormone systems.
The critical insight here is that the chemical property that makes the polymer so useful, its durability, its inertness, is precisely what creates this massive long-term environmental and potential health burden when we throw it away.
Yeah.
It's the ultimate trade-off of synthetic chemistry.
Okay, so let's move from the structural integrity of materials to the chemical stability of consumables. Let's pivot into Deep Dive 3, the chemistry of food preservation. We're going from engineering a permanent structure to engineering temporary stability.
And again, definitions are key here. Food preservation is basically subjecting food to some kind of physical or chemical treatment to prevent or slow down spoiling.
And a food preservative is the substance itself, often an engineered chemical, that you add to food to stop microbial growth